Hello, hello. Okay. There we go. Yeah. Good morning, Zhao. Pleasure to be here with you all. I hope you're all doing well. My name is Chris. I'm the head of partnerships at BTQ. Very excited to be here today to talk a little bit about the future of zk, specifically around challenges, advancements, and tooling for the development of post-quantum zk-SNARKs. Before we get started, there is a QR code here. This is the hack MD for this talk. I believe this is where you can collaborate over notes. And yeah, we can get into it. Also want to do a quick survey just to get to know the audience a little bit. So please raise your hand if you are a zk researcher. zk researchers? Nice, a few of you. And then how about zk developers? Nice. Okay, great. Okay, I think I'm in the right place then. So the outline for today's talk will be introducing a little bit about our team at BTQ and the work that we're doing in post-quantum cryptography, using PQC as a motivation for why we think we need to start thinking about this transition to post-quantum SNARKs. I'll introduce Keelung, which is our team's attempt at initiating this transition to PQ SNARKs, talking a little bit about the language and the ecosystem, and then finishing up with a live demo. So our team at BTQ was founded by a group of post-quantum researchers with an interest in addressing the threats that quantum computers pose to blockchains. We conduct research in both software and hardware, and really what we're looking at is how to make PQC more manageable, more digestible in industry, blockchains and other technologies. And in our effort to do so, this has led us down the rabbit hole of post-quantum SNARKs. So let's talk a little bit about that today. So for those of you who aren't familiar with this idea about post-quantum cryptography, let's distinguish how this differs from pre-quantum cryptography first. So pre-quantum crypto is most of the cryptography we use today, which relies on mathematical problems that are assumed to be difficult only by the computers that we have today. So most of the problems that underpin our crypto systems that we rely on being difficult are things like factorization of large numbers. This is what you find in the RSA crypto system. Also the discrete log problem, which you find underpinning elliptic curve cryptography. Now the problem with pre-quantum cryptography is that these problems aren't necessarily hard for quantum computers to solve as well. And so if there was a quantum adversary, they'd be able to essentially solve these problems which underpin the crypto systems that guarantee their security. So what we need to do in post-quantum cryptography is look to swap out these problems that we assume as being difficult that underpin these crypto systems. And so we can look to kind of new variations or new fields of cryptography, namely lattice-based and hash-based. These are two very popular fields in post-quantum cryptography that introduce new problems that there are no known efficient quantum algorithms for. It's also worth noting that lattice-based and hash-based cryptography underpin the latest NIST standardized algorithms, which is the standardizations body in the US, which essentially dictates what all government organizations need to use. And so it's really seen as the de facto class of cryptographic algorithms to use. So a lot of people are looking at lattice-based and hash-based cryptography. Another way that we can look at this transition to post-quantum cryptography is from the point of view of complexity theory, where right now we're relying on problems such as integer factorization, a discrete logarithm problem. But unfortunately, these problems lie within the space of BQP, which is the set of problems for which there are known efficient quantum algorithms for. And since we are on the horizon of quantum computers, it's now the time to move out of BQP. We want to replace these problems with problems such as learning with errors and the short integer solution, both of which are found in lattice-based cryptography, for example. And since SNARKs are really just cryptography under the hood, this means that there are also pre- and post-quantum SNARKs. The good thing is that post-quantum SNARKs do exist. So this taxonomy of SNARKs was taken from Justin Thaler's book on SNARKs, and he's identified several plausibly post-quantum SNARK constructions. So there is hope, and what this talk is going to be about is how do we initiate a transition to using these post-quantum SNARKs, or like how do we make this transition as painless as possible. This transition to SNARKs is also on the Ethereum roadmap, and quantum safeness is very much the end game in Ethereum, as it should be in pretty much every cryptographic or any like digital technology that uses cryptography. So I'm not sure if you can see this, but on the long-term roadmaps, you have quantum-safe aggregation or aggregate-friendly signatures, quantum-safe setup-free commitments, and down here we have transition to quantum SNARKs or quantum-safe SNARKs. What we should also acknowledge is that this transition to a fully snarked Ethereum is underway. So this is the item down here where we have a fully snarked Ethereum, and we're already starting to see this via the emergence of zk rollups, zk EVMs, zk indexers, zk oracles, zk just about everything. And what this means is that with all of these zero-knowledge proofs, we're also going to need to upgrade those to post-quantum zk. And a final note here is that, just referring back to the other slide, I think a common misconception is that SNARKs are like the only way out of this forest of pre-quantum, but there do exist post-quantum SNARKs as well. And so what we'll end up with is having a variety of options for post-quantum zk SNARKs, just as we do today. And you'll most likely want, or you'll be able to pick the SNARK that fits your application, that affords you the correct trade-offs based off of your requirements. And so starting to think about how we live in a I guess multiple post-quantum SNARK world and how we can move between them. So in our effort to start initiating this transition to PQ SNARKs, our team has developed Keylung, which is not not a coincidence that it's a Taiwanese go Taiwan Taiwanese city, and Keylung is a zk DSL for writing zero-knowledge proofs. What we aimed to do with Keylung was to make it as easy as possible for developers to write secure and reliable post-quantum SNARKs without requiring significant expertise in cryptography. Keylung is also 100% open source, which we're very pleased to say. There are two components of Keylung. There's the language, which is currently 100% open source. There's also a compiler, which we'll talk about, which we'll be open sourcing in the next several months. We're also very excited to launch Keylung with some of our launch partners in CISIC, who's working with hardware acceleration, DMTP, Holonym, and VES. Great. So when we went about building Keylung to, again, initiate this transition to post-quantum SNARKs, we recognized that building another zk DSL maybe wasn't the hottest thing to do because there are already so many great DSLs out there. So in addition to supporting post-quantum, we also made an effort to support some other things as well, such as mobile witness and proof generation, which we think is critical in order to onboard the next million of users into crypto. Obviously supporting a variety of post-quantum proving systems and also implementing post-quantum cryptographic primitives in our Keylung library for developers to use. We also will support a variety of pre-quantum proving systems as this kind of bridge for developers to start with pre-quantum and then move to post-quantum, which we'll talk about in a bit. We also wanted to make this as developer-friendly as possible. So we raised the level of abstraction required to build these circuits so that you don't need to be a hardcore zk developer nor cryptographer in order to build safe SNARKs. And then we also are working on hardware acceleration, tighter integration with hardware acceleration with our partners at CISIC. So the idea behind keylung is that you can write one circuit and live with it for the rest of eternity. So in this diagram here, you start off with writing your circuit description in keylung, which then gets compiled down to kind of like a pre-intermediate representation in ETHTaipei, which will essentially be able to route it to various back-end proving systems. And we really think that this is one of the ways that we can go about initiating this transition, where if you're a developer, you can write your circuit description once and then just recompile it back to it, or recompile it down to a post-quantum proving system when you think it's time for your application to upgrade. So we'll talk a little bit about keylung and how we try to make it easy for developers to build these quantum safe SNARKs. So we made maybe an interesting design decision in embedding keylung in Haskell. Is anybody here a fan of Haskell? Any fans of Haskell? Yeah, nice. Whoever's a fan of Haskell, their arms just shoot up when I ask this question, so I love it. It's a loyal community. And so essentially, by embedding ourselves in Haskell, we get to inherit a lot of Haskell's functions, module systems, libraries, functionality, which makes it really, really elegant and really easy to express some circuit descriptions in as little effort as possible, and also in a very safe way. When we focused, so we embedded ourselves in Haskell, and when we went about building the actual zero-knowledge components in Haskell, we actually realized that it was actually a relatively small language that we needed to maintain in order to make zk generation or zk proof writing possible in Haskell. So we have a relatively small core language, which we'll actually run through today, and then also a very simple interface for bridging keylung and Haskell. Something that I've noticed when programming in keylung is that it's actually very clear when you're writing Haskell and when you're writing keylung, because most of the heavy lifting is done by the Haskell language. Like most of the computation or the description of the computation that you want to do is done in Haskell, and keylung really just looks after the management of like your public and private inputs. Keylung also has a compiler, which I briefly mentioned. So every keylung program gets compiled down to a set of constraints, which will then be fed to either pre or post-quantum proving systems. And this is something that we've put a lot of effort into as well. So in our compiler, every program will go through a series of optimization passes, basically in order to reduce the number of constraints as much as possible before it gets translated into its relevant IR. Okay, so touching on the small core language of keylung in order to develop these PQ SNARKs, really you only have to keep track of three things, or three data types, which are field elements. These are just numbers in a finite field. Booleans, which are really just finite field elements, field elements underneath the hood, but allows you to express things like true and false. And then unsigned integers, which gives you a little bit more of expressivity when you're building these circuits. So before we dive into some more interesting examples using keylung, let's just start with a very simple example using the square function to get us kind of familiar with keylung. So the square function accepts a public input x, a private input y, and then asserts that the private input is the square of the public input. And when we're thinking about developing SNARKs, we just want to get into this mode of thinking about public and private inputs, because recall that zero knowledge, you're typically trying to prove something about some computation or about some information without fully disclosing that information. So the public input is what you're willing to share with the world, and the private input is what you want to hold close to your chest. So I think this example is really nice. Is a really nice way to see how, or to see the benefits of embedding a zk DSL in Haskell. So in this example, we're going to walk through how we can think about implementing the rounds of a Poseidon hash function. So Poseidon is a hash function that was designed specifically for zero knowledge proofs, which makes it very, very fast. And so typically, if you're going to be hashing something in a snark, you're going to be looking at using the Poseidon hash function. The reason it's so fast is because it uses a substitution permutation network design where it consists of several instances of these rounds, which are the implementation of the same set of functions, and it just essentially permeates through this network. So if we were to think about implementing one of the rounds in Poseidon, assume that we have the relevant functions at each one of the steps. So we've already implemented arc, s, and m. And so to define the round function, we would just use the Haskell notation and define round, which takes, looking at the top row here, the first line here, which takes an integer as input, a list of field elements as input, and then outputs a list of field elements. And then for the actual function definition, we can say that one instance of this round to R, which will be this integer. So the integer is this input here to arc. Well, it's the input to R, and then arc will take the list of field elements. It'll compute that, use the output of arc as input to the sbox function for that round, and then use the output of that as input to the mix function. So if we were to think about, let's say that we wanted to implement 3 of these rounds. If we were to express this mathematically, it would simply be to just compute the first round, round 0, against some initial state of data, and then use the output of that as input to the first round, and use the output of that into the input as of the third round, which is just these nested functions. And we can do all of this really elegantly in Haskell using the fold-L function. So this gives you a glimpse of how expressive writing zk-SNARKs can be in Haskell. And building on this idea, we're able to implement fairly sophisticated things in Keylong using very few lines of code. So this is an example of proving Merkle tree membership in Keylong in 9 lines of code. Okay, so getting started with Keylong is actually very, very easy. We have a GitHub code spaces, which there will be a QR code at the end, which you can find. That'll navigate you to our Keylong examples repo. And this allows you to essentially hit code, then go to code spaces, and then there will be a plus icon here to launch a new code space. And it'll pop up with a VS Code environment that looks just like this. Our credit card is just down. We're just changing it right now, so we don't have the plus icon, but it's typically here. But once you launch a new code space, you'll see, you'll have a VS Code environment that allows you to essentially play around with constructing these snarks, which you can start off as being pre-quantum and then later compile back to down to a post-quantum proving system. So maybe just to run through some examples, just to get us familiar with Keylong. We have a very simple echo function here, which takes x as a private input and returns x. So let's see if I can run this. I'm just going to sit down. OK. So in order to interact with Keylong, we can just navigate to the terminal and open a REPL. Can you hear me? Does this work? Yeah? OK, thanks. Great. And now we're in the REPL, and now we can actually start playing around with some of these functions. And remember, you can do all of this in the GitHub code space. So we can start with GF181, which is the finite field that we've chosen to construct the circuit. And you can change the finite fields, and this gives you different security parameters. So we'll start with GF181, and then echo, and then, which is the name of the function. And then in Keylong, the first set of bracketed parameters is the public input, which we'll leave empty. This doesn't take any public inputs. And then we can put in a private input 3, and it will just echo the private input. We can also do something like square, where this time we will have both a public and private input. So we'll go GF181, square, we'll go 3 and 9. And this will compile. It'll essentially assert that the private input was a square of the public. Whereas if we did something that didn't, a private input that wasn't the square, it just wouldn't compile at all. So maybe now we can move on to a more interesting example of proving something that we might actually want to prove in the world, which is maybe that we're old enough to drink, at least in the US. And this should actually be proof that I'm greater than or equal to 21, but that's a minor detail. Okay, so to construct a SNARK to prove this, we'll just need a few pieces of data. We'll need my birthday, the minimum age, or the minimum age that I need to have lived in order to have a drink, and then today's date. And from those 3 pieces of data, we can construct M and N, M being how old I am, and then N being how old I need to be. And we just want to prove very simply that M is greater than or equal to N. So in Keylong, we've written a very, very simple function called check minimum age. And what this will do is it essentially just pulls on like a very simple script, let's say this birthday script that generates, basically the M and N here. So here we need to be at least this many days old. So we'll go back to the REPL, GF181, check minimum age, and here it accepts a minimum age as a parameter. So we'll go, I need to be at least this many days old, and then no public input, and then a private input here. And this will compile, and it'll generate a proof for you that you can then walk around with and go to any bar and say, hey, cryptographically verify that. You can cryptographically verify that I'm old enough to have a drink here, and they have no option but to give you your favorite drink. Of course, if we change the minimum age to, let's say, being like 45 years old, so I just used my birthday, and I'm not quite 45 yet, but it just won't compile. And so this is a very, very simple SNARK that we can essentially put in the hands of, let's say, like a trusted verified issuer in order to create these proofs for us on behalf of us that we can then walk around to different places and prove our age without needing to be embarrassed sometimes maybe about how old you are. Yeah, and that wraps up my talk. So thank you very much all for your time. I appreciate it. Yeah, thank you.
Anyone has questions?
Why Keylong, not Taipei?
Yeah, so that was our chief architect was just, I think he was inspired by the river in Keylong and felt that there was some connection with zero knowledge. I think he's operating at a higher level than I am in terms of his inspiration, but he was inspired very much by Keylong, yeah.
How does the performance compare to the existing solutions?
Yeah, great question. Yeah, so we've benchmarked
prover time and verifier time.
Yeah. So typically those are influenced by the number of constraints. So the prover time is impacted by the number of constraints that you have. We're competitive with Socrates and Circum. Pretty much all of the major DSLs have benchmarked like a certain number of constraints for certain implementations, and we meet those requirements. So it's less about being like more performant, and then we've shifted our focus to being like easier to use and having this flexibility to post-quantum. Mm-hmm. Yeah, thanks.
Any questions?
Yeah, so basically the developer don't need to write the code in like RNCS or other constraint system form, right? Because the Circum has to write in RNCS, per my understanding.
Yeah, sorry, yeah. Also, it's kind of hard to hear. Was the question, sorry, do you mind repeating the question? I'll just come closer.
Oh yeah. So my question is, with Keylong, then the developer don't need to write the code in the R1CS or other constraint system compatible form, right?
I see. Okay, yeah. 1 sec. Let's go back up to. Okay, so the question was whether developers need to write in the actual intermediate representation, which R1CS is one IR. There's also a Planckish IR, and then. So the answer would be no, they can write in a high-level language, such as Keylong. And this is typically the case for most languages. You typically write in some high-level circuit description language, such as like Cairo, Socrates, Circum, and then it gets compiled down to the IR. So all of the work is being done just at the high-level language level. Does that answer the question, or?
Yeah.
Okay, cool, thanks.
Okay, I'm curious about how large is the differences between pre-quantum proving system and post-quantum proving system. I mean that Keylong is amazing that providing some useful syntax for writing the circuit than Circum or other language. So I'm curious about how is it much worse to creating another compiler to deal with the IR and then compile the IR into post-quantum cryptography than just creating a new language such as Keylong?
Okay, yeah. I think there's a few ways I could go about answering this. First of all, there are trade-offs when you use post-quantum provers. They typically are more expensive. They take more time to generate, and then they're also typically larger. So that's one of the things that you deal with. And then I think there was like a part of your question, I think, well, that at least I understood, which is like, are there trade-offs in the IR and basically the efficiency of compiling to like different IRs based off of which prover you want? And at least in the OpenZL architecture, there's like an intermediary phase here where after your circuit description goes through this essentially a routing software to the appropriate adapter, it'll go through a series of optimization passes specific for that prover. So for example, there would be an R1CS specific optimizer and then a Planckish optimizer. And yeah, I honestly can't say whether the optimization or optimizing constraints for different constraint systems seems to be like kind of where the state-of-the-art research is right now, at least in the compiler design. So I'm not aware of like how competitive this solution is to just like native optimizers, but I would imagine that like in this design, the idea is just to implement the state-of-the-art optimizer in this stack here. So it should be competitive. Yeah.
Okay, let's thanks to Chris again.
Cool. Thank you.